I am going to discuss the resonant circuits. Both series and parallel resonant circuits will be analyzed. Resonance is the condition when, say, the frequency of oscillations coincides with the natural frequency of the system. This particular has been experienced in the mechanical system as well. At the resonance, the system responds in the greater amplitude. This situation may destabilize the whole system and the mechanical system may be permanently damaged. Our focus is on the electrical system aspects. It is the condition for the maximum power delivery or absorption. It is used in the electrical system in the tuned circuit where we will be selecting a specific frequency from the spectrum of the frequency. Under this particular condition, the power transfer is coming out to be maximum. Phasor relations of the current and voltage of different circuit elements. We have gone through this elaborately in the previous discussions where say we analyze the series and parallel AC circuits. So as a recap, VR is equal to IR into R. So that suggests that the voltage across the resistance is in phase with the current through the resistance. For the inductor, VL is equal to J omega L IL. So that suggests that the voltage across the inductor leads the inductor current by 90 degrees. So this 90 degree is coming out because of this J operator. For the capacitor, similarly, the voltage across the capacitor lags the capacitor current by 90 degree. So as discussed previously that to have a resonance we have to have a source of the varying frequency. So that particular source is considered as the sinusoidal AC source and another arrangement which is resulting into the natural frequency. So the system natural frequency in the RLC circuits are governed by the inductance and the capacitance. So we will be analyzing the RLC, you can say the circuit consisting of RLC elements. However, when say the resistance approaches to 0, the circuit will result into the LC circuits. Likewise. At the resonance, the circuit behaves as resistive whether it is a series or the parallel arrangement. So that particular we will be discussing and will be exploiting also in the details. Now the first aspect of this particular resonance circuit is to calculate the resonant frequency and then find out the other parameters of interest likewise. So as mentioned that we are going to discuss the series RLC resonance and the resonance in the parallel RLC circuits. Thereafter we will be making a comparison of the series and parallel resonant circuits likewise. So the parameters of interest are the resonant frequency, the Q factor, quality factor that is, the bandwidth and the half power frequency. So bandwidth is coming out to be omega 2 minus omega 1. So there is a relation between the half power frequency and the bandwidth likewise. So we will also be coming out how these particular parameters are interrelated as such. So in case of the series resonance circuit, series RLC circuit, this particular is a source of having a fixed magnitude V, but the frequency is varying and the R and RLC they are connected in series. So the KVL suggests supply voltage has to be equal to the VR plus VL plus VC. We have already discussed the phasor relationship. Here say the current is common. So the expression comes out to be I R plus J omega L minus J upon omega C. This omega L is the inductive reactance. 1 upon omega C is the capacitive reactance. So this particular is resulting into the form like this. The current into the phasor form can be written as V angle 0 upon Z angle theta. So Z angle theta is the polar form of representing the impedance. So while say we have written Z angle theta, so we have considered that XL is greater than XC in this. So these are the expressions to define the impedance magnitude in terms of ohms and the theta impedance angle. Now the variation is plotted here. So as say the impedance is having three components: resistance, then the inductive reactance XL, and the capacitive reactance 1 omega C. So this particular is plotted with respect to the frequency. Resistance is constant, that is not changing. XL, that is equal to omega L, so that is linearly increasing with the frequency. Likewise, XC is equal to 1 upon omega C, so that particular is having an inverse relationship as such. And Z, which is plotted likewise when expressed as root of R square plus XL minus XC square. So what we will be seeing that at this specific frequency, which we have designated as omega 0, the impedance is minimum, and that value is exactly equal to the resistance. Corresponding to the left side, which is the omega less than omega 0, the capacitive reactance is dominating to the inductive reactance, so the effect will be capacitive. The nature of the circuit will be capacitive. Likewise, when say omega is greater than omega 0, some point on say this right side we are considering, then XL is coming out to be dominating than XC, so the nature of the circuit will be inductive. Likewise, so when say it is said that the nature of the circuit will be inductive, if we are calculating the current at this omega greater than omega 0, it will be of lagging nature. So exactly at omega is equal to omega 0, inductive and the capacitive reactances are identical, so they will be cancelling out each other, and the resulting impedance will be resistance, and the behavior of the circuit will be resistive. So this is the condition which is regarded as the resonance condition, and the omega 0 is equal to the resonance frequency. So same thing, whatever has been depicted, explained previously, that particular is demonstrated here. So at resonance, XL will be equal to XC. They are substituted likewise. So this particular is happening at a given frequency omega 0. So instead of omega, we will be substituting omega 0. Omega 0 is therefore calculated as 1 upon root LC. Now this particular is a phasor diagram. So as say the current is common, that particular is marked. Voltage across the resistance is in phase with the current, so that particular is VR is marked. VL, which will be 90 degree leading to the current, VC will be 90 degree lagging to the current. So what we will be seeing that VL is of exactly equal and opposite value of the VC, so they will be counterbalancing, and therefore the supply voltage will be appearing across the resistance. So what we can make a summary that XL is equal to XC for series RLC, circuit behavior is resistive, impedance is minimum, Z is equal to R, that we have seen. When say the impedance is minimum, the current will be maximum, supply voltage is appearing across the resistance, and important observation here as well that VL is equal to VC, so that suggests that at omega 0 the series LC combination acts like short circuit. So what is the meaning of short circuit? That when say we are taking LC as a combination, the net voltage across that will be 0 likewise. However, please be mindful that when say the full voltage is appearing across the resistance, it does not suggest that the either VL is equal to 0 or VC is equal to 0. They are having say the specific even higher value than the supply voltage likewise. So here say the another term which we have to associate, that is a quality factor. So quality factor is basically to measure the sharpness of the resonance curve. At resonance, what is happening that the energy is keeping oscillating from the inductor to the capacitor or capacitor to inductor likewise. To measure it, fundamental definition is that the quality factor relates the maximum energy stored to the energy dissipated per cycle of oscillation. However, for clarity, you can have that in case of series RLC circuit, the Q factor is nothing but VL upon V. This V is basically appearing across the resistance, so you can say VL upon VR. Similarly, VL is identical to the VC, so the Q factor can also be designated as VC upon VR. So when say we are making a substitution, the Q factor is coming out to be omega 0 L upon R, or conversely 1 upon omega 0 CR. So here say we have simply substituted XL and XC values in the calculation. Now what we will be seeing here, that when say it is to measure the sharpness, so you can easily see that this particular curve which is represented at top is having a sharper than compared to the second one, compared to the third one. So at this particular, although say the resonant frequency are coming out to be the same, but the Q factor of this is highest compared to this. The Q factor Q2 is higher than Q1 likewise. So here say the B1, B2, B3, they are associated with the bandwidth that we will be discussing in the subsequent slides. Now as mentioned, that at resonance the current is maximum, and that particular current will be nothing but decided by the Vm upon R. So Vm, let's say, is the peak value as such. Now this Vm by R, so at this the current is maximum. Now we are considering the two situations. One is in the capacitive region, other one is in the inductive region, where say the current is coming out to be exactly the maximum current upon root 2. So the purpose of this is that corresponding to this particular current, the power delivered will be half of the power that is delivered at the resonance. So that's why the name is given as half power frequency for omega 1 and omega 2. Another point here is, in this particular range of frequency, or in this particular band of frequency omega 2 to omega 1, the current is always greater than or equal to I max upon root 2, or you can say 70.7% of the I max. So when say the current is coming out to be 1 upon root 2 times of the maximum current, so that suggests that the impedance has to be root 2 times of the impedance at the resonance. So at the resonance the impedance value was R. So this particular is suggesting we can rearrange the term. You can have the value omega L minus 1 upon omega C is equal to plus minus R. So here say the plus minus sign of this resistance is important, and that has to be analyzed. At omega 1, the nature of the circuit is capacitive, so the net impedance is coming out to be negative R. So we will be keeping this minus sign for the capacitive region, or you can say the lower half power frequency. Similarly, this is the upper half power frequency, and the positive sign is considered. Here say the behavior will be inductive likewise. So let's say this particular is resulting into the quadratic equation, and that roots are explained, so that particular is suggesting omega 1 likewise. So if suppose we are making a comparison with the standard equation ax square plus bx plus c is equal to 0, that particular is resulting into the two roots minus b plus minus root of b square minus 4ac upon 2a. So that plus minus sign is to be discarded because the frequency cannot be negative. So here only the plus sign is considered. So the omega 1 is expressed like minus r upon 2l plus root of r upon 2l square plus 1 upon lc. Similarly, you can calculate the omega 2 while considering the positive sign on this particular side. Now what we will be seeing, that the bandwidth omega 2 minus omega 1 can be directly calculated, and that particular is given the value r upon l. With these particular numerical expression, you will find that omega 0, which is the resonant frequency, is the geometric mean of the half power frequencies omega 1, omega 2 likewise. So omega 0 is equal to root of W, you can say omega 1, omega 2. Now the quality factor we have already defined, that is omega 0 L upon R. Bandwidth has come out to be R upon L. So this particular is resulting into the expression Q is equal to omega 0 upon B, or you can say the resonant frequency upon bandwidth. So as say the bandwidth is narrowing, decreasing, the Q value will be increasing likewise. So Q is the ratio of resonant frequency to the bandwidth. Now this Q is substituted likewise in these expressions. So we will be resulting into the expression of the half power frequency as omega 0 square root 1 plus 1 upon 2q whole square minus plus omega 0 upon 2q. So simple substitution is working to obtain this particular expression. So this particular Q we previously correlated with the 3 different Q parameters, and that particular is suggesting something to define the selectivity. So the selectivity of the RLC circuit is the ability of the circuit to respond to a certain frequency, or you can say to discriminate against all other frequencies. So basically when say we are interested in selecting the narrow band of frequencies, then the circuit Q must be high. Now if suppose say the circuit Q is coming out to be greater than 10, then that particular is regarded as a high Q circuit. So for the high Q circuit, if suppose you are having this particular expression which we discussed in the last slides, then we will be simply substituting the Q greater than 10. So this contribution is approaching towards 0. Because of that, this is resulting into only the omega 0 value. Other aspect is we have substituted we can make a substitution of omega 0 upon q as bandwidth. So this particular equations are coming out to be like this: omega 1 is equal to omega 0 minus b upon 2, omega 2 is equal to omega 0 plus b upon 2. So it is suggesting that for a high Q circuit, the half power frequencies are symmetrical about bandwidth and the resonant frequency. Now having discussed the series RLC in detail, now we can quickly go through the parallel RLC circuits. So they are connected in parallel. In case of series RLC, we have considered the voltage source. So as a, you can say, the analogous source transformation aspect, we have to consider it as a current source likewise. Now we will be applying the KCL. So the input current, source current is equal to IR plus IL plus IC. What we have seen that in case of parallel, the voltage is common. So this particular IM is expressed like this. Now 1 upon R is referred as the conductance. So similarly, this particular is coming out to be capacitive susceptance. This is the inductive susceptance likewise. So the term is yielding to this particular nature. Now you can easily make a comparison that in case of series RLC, we obtained Z is equal to R plus J XL minus XC. So the simplified expression can be analyzed likewise. Now in this particular, the resonance condition will hold true when say this reactive term is coming out to be 0, and that particular is possible BC is equal to BL. So the resonant frequency is the same, that is coming out to be 1 upon root LC for the parallel RLC circuit as well. However, the voltage will be maximum because the supply current will be passing through the resistance. So whole of the supply current is passing through the resistance likewise. So Vmax is expressed INR. Now on the analogous line, you can say this particular is a voltage which is taken as a reference. So current through the resistance is in phase with the supply voltage, that is marked along this. Current through the inductor is 90° lagging, so that particular is marked likewise. Current through the capacitor is 90° leading to the voltage, so that particular is marked At the resonance, IL will be equal to exactly IC. So this particular will be I, which is equal to IM is equal to IR likewise. So on the analogous line, if suppose we are considering a frequency lower than the resonant frequency, BL will be greater than BC and the behavior will be inductive. At resonance, the behavior will be resistive. For the frequency greater than resonant frequency, the behavior will be capacitive likewise. So as a summary of the few salient points, that at resonance BL is to be equal to BC, circuit behaves as resistive as we have seen in case of series RLC. The admittance is minimum, the voltage is maximum, that value we have calculated Im into R. Supply current passes through the resistance, the current IL will be IC. So when say these two currents are identical, they are cancelling out each other in the resonance. So that suggests that the parallel LC combination acts like open circuit. In case of series, the series LC combination was acting as short circuit likewise. So as mentioned that although it is acting as an open circuit, but that doesn't mean that the IL is equal to 0 or IC is equal to 0 likewise. The Q factor, as we have defined previously as voltage amplification, so here it is defined as the current amplification factor. So Q is equal to IL upon IR, that particular is substituted likewise R upon omega 0 L. Similarly, you can define the Q factor as IC upon IR, so that particular is giving rise to the omega 0 RC. So here the Q factor are coming out to be, you can say, having a reciprocal relationship, whereas the resonant frequency is having the same expression omega 0 is equal to 1 upon root LC. So at half power frequency, the voltage will be Vmax upon root 2, then only the power transfer will be half. So correspondingly, the condition will suggest that admittance has to be root 2 times of the admittance at the resonance. So on the analogous line, you can plot it likewise. Here what we will be seeing that the omega 1, which is the frequency lower than the resonant frequency, the behavior of the circuit will be inductive as such. At omega 2, frequency above the resonant frequency, the circuit behavior will be capacitive likewise. So when say we will be solving by the procedure listed out previously, the bandwidth is calculated again as omega 2 minus omega 1 is equal to 1 upon RC. So that particular is still coming out to be bandwidth is equal to the omega 0 upon Q, or you can say the quality factor is the ratio of resonant frequency to the bandwidth likewise. So on the similar line, you can approach for the half power frequency in terms of the quality factor and the resonant frequency likewise. So that particular is to be analyzed on the say analogous line. Between this bandwidth, or you can say the frequency omega 1 to omega 2, the voltage is coming out to be greater or equal to 70.7% of the voltage at the resonance. Now as a comparison of the characteristic features of the series and parallel resonant circuits, so it is providing the summary as such. We have calculated the resonant frequency for both. It is having say the same numerical expression 1 upon root LC for both series and the parallel. The quality factor which we defined for the series as VL upon VR, so that is resulting into V, you can say omega 0 L upon R term, where say for parallel it is the IL upon IR, so it is resulting into the term R upon omega 0 L. So there is a inverse relationship between the quality factor. However, the bandwidth is the same as the ratio of resonant frequency to the quality factor for both series and parallel. Similarly, the half power frequency can be expressed likewise by the similar relationship, and for the high Q, the circuit for say high Q circuits, where the quality factor is greater than equal to 10, the half power frequencies are symmetric about the resonant frequency, and they can be expressed directly as omega 0 minus b by 2 and omega 0 plus b by 2 likewise. Now we can go through some of the examples likewise. So this particular is typically different from what the case we analyzed previously, but it is a RLC circuit, and the first requirement for calculating the resonant frequency, that the behavior of the circuit has to be resistive. So by the series parallel combination, you will be calculating the net impedance. So you have calculated the admittance offered by this RC combination as such. So that is coming out to be like, its reciprocal is calculated, so that is giving us the value of ZRC. Now the net impedance experienced at the source is calculated, so that particular is evaluated likewise. Now to at the resonance condition, the net impedance, or you can say the imaginary component of the net impedance, has to be 0, that is calculated likewise. So the resonant frequency is coming out to be 2.179 radian per second for this circuit. This particular is the series RLC circuit, where say the resistance value is specified, inductance value, capacitance value is specified. We have to calculate the resonant frequency and half power frequency, the quality factor, bandwidth, the amplitude of the current at resonant frequency and the half power frequency. So all parameters are to be calculated likewise. So the resonant frequency is 1 upon root LC, that is calculated as 5 into 10 to the power 4 radian per second. The quality factor, we can make use of omega 0 L upon R, or you can say 1 upon omega 0 RC. So this particular is giving the same value 25. The bandwidth is nothing but ratio of resonant frequency to the Q factor. That particular is calculated as R upon L, so the value is 2 into 10 to the power 3. Now what we will be seeing, that the quality factor is greater than 10, so we can easily estimate that the half power frequency will be symmetric about the resonant frequency and dispersed by half of the bandwidth on either side. So that particular is calculated as 49 kiloradian per second and 51 kiloradian per second. Now the current at the resonant frequency, that particular will be decided by this particular, so that is a Vm upon R, so 20 by 2, 10 ampere. Current at the half power frequency will be 1 upon root 2 times of the current at the resonant frequency, so that particular is giving us the value 7.07 ampere. On this we can make some summary points, that whether the circuit is of series nature or parallel nature, it behaves as resistive under the resonance. So the resonance is a condition which is achieved when say the frequency is varying, whereas the element's value is kept unchanged. So this particular is more important because the behavior of the circuit is resistive, or you can say it is maintaining the unity power factor, but this is coming out to be different than the power factor correction, which we will be discussing in the next class. The resonant frequency is the same, that is 1 upon root LC for both series or parallel RLC. The quality factor must be high if the band of frequency to be selected is narrow. Series combination of LC in the series resonant circuit behaves as a short circuit. So short circuit means that with this series combination, the voltage across LC combination will be 0. It is not suggesting that the voltage across the inductor is 0 or the voltage across the capacitor is 0. So because the voltages are of opposite nature, that's why the effective summation is coming out to be 0. Similarly, the parallel combination of the LC in parallel resonant circuit behaves as open circuits. So, in the next we will be discussing the power factor correction and resonance in the tank circuit. For further reading you can refer these textbooks. Thank you.